Good afternoon, everyone, and welcome from me as well to the second RISC-V meetup in Duisburg, even though we are not actually in Duisburg, but rather in this online meeting. But I hope we're going to have a good day anyway with some interesting talks. And today I would like to talk about post-quantum cryptography on embedded RISC-V hardware. So my name is Jan Thoma. I'm a PhD student at Ruhr University Bochum at the chair for security engineering, and our chair works with security research in the field of side channels, fault attacks, secure architectures, and post-quantum cryptography. And the talk today, I will focus on a project we have here since 2019. It is the QuantumRISC project, and it is funded by the German Federal Ministry for Education and Research. And in this talk, I would like to introduce you to the topic and also provide some details on what we're doing. So as you can see here, our partners are mostly from the automotive industry, as represented by Continental, Electrobit, and MTG. And also some academic partners, including the Fraunhofer SIT, the Rhein-Main University of Applied Science, the TU Darmstadt, and of course the Ruhr University where I'm located. So what do we do in this project? We develop flexible solutions for long-term security, and as I said, we're mostly in the automotive context, and therefore we focus on stuff like control units, infotainment systems, and also safety features like car-to-car communication, and how to secure that in the long term. And therefore we chose a RISC-V development platform because it enables us to implement dedicated hardware accelerators and integrate them deeply into the control units. And since most of the use cases are in the embedded environment, the RISC-V platform overall just is a pretty good fit. So to start with, I would like to motivate what post-quantum cryptography is and why we care about it. And since this is a RISC-V workshop rather than a cryptography workshop, I'd like to begin with introducing the current environment in cryptography. So basically, as most of you probably know, there are two different types of cryptography. The first of which is symmetric cryptography, and that is where we have one shared key, which is used for encryption and decryption. And you have to share the key with both communication partners before you can use it. And I guess you all know symmetric cryptography from AES, DES, and probably less common, the present cipher. And that is working pretty well, but of course there's one problem. If we have to use a pre-shared key, then how do we share this key? Because if we do it over an insecure channel, we don't need to go through the trouble of encrypting in the first place. So therefore, we have the second class of cryptography, which is asymmetric cryptography. And there you have two keys, one for encryption, which is the public key, and one for decryption, which is the private key. And as you can see in the graphic here, you use the public key to encrypt the data. So everyone knowing the public key can encrypt data, but only only persons knowing the private key can decrypt the ciphertext. So it is not possible to decrypt the ciphertext using the public key. And I guess most of you also know some examples for asymmetric cryptography. Probably most common is RSA, but also all of elliptic curve cryptography, and also like digital signatures like DSA is also asymmetric cryptography, and the Diffie-Hellman key exchange as well. And what all these asymmetric schemes have in common is that they are based on a hard mathematical problem, such as factorization or the discrete logarithm problem. And there are usually security proofs that reduce the security of the scheme to the underlying mathematical problem. So you can say RSA is secure if the factorization problem is hard. And that is pretty nice as long as the factorization problem is actually hard. But there is a new threat coming up, and that is quantum computers. So for symmetric cryptography, the security is roughly halved if a sufficiently large quantum computer exists, and that is due to the Groover algorithm. But even worse, for the asymmetric schemes, the mathematical problems on which most of these schemes rely can efficiently be solved using the Shor algorithm. And what that means is for symmetric cryptography, we are okay-ish. So usually we use, for example, AES 128. And since the security is halved, we need to double the key length. So we can use AES 256 and we're fine. But basically the complete field of asymmetric cryptography as we know it today will be broken once a large quantum computer exists. And large means like 1000 qubits, probably a little more. And you probably have heard that Google lately announced quantum supremacy, and they have like 60-ish qubits, so it's quite a long way to go actually still. But the question, of course, is how long will it take until we have such a quantum computer which is large enough to be harmful to our cryptography? And so these statements are all like from 2015 to 2020, and they make guesses on when a quantum computer will be built that is large enough to break our cryptography. And the PQ Crypto project says that it will be sometime after 2025, so starting in 5 years or something. And Google says it's even earlier, so 2020 to 2025, which is actually pretty much now. And also the NSA suggests to initiate a transition to quantum resistance algorithms in the not too distant future. And we should all have learned that if the NSA suggests that we should do that, then it's probably about time to actually do that. So problem, of course, is we need new algorithms because we cannot just scale up RSA and then have an efficient cryptographic scheme that is secure against quantum computer attacks. And therefore, the NIST most prominently started a competition for quantum secure signatures and encryption schemes. And this is currently in round 3, so the finalists are selected, but there is no like final standardization that came out of it, but it's supposed to happen pretty soon, so probably next year or something. The current state is that there are 4 finalists for key establishing mechanisms, which is like comparable to encryption, but actually it's just to establish a key that can then be used for symmetric cryptography. And then there are 3 finalists for digital signatures, plus some other alternative candidates that can be used if it turns out that the finalist algorithms aren't secure or can't be used for some other reason. The BSI, so Bundesamt für Sicherheits in der Informationstechnik, is actually a step further and already recommends PhotoChem as the key establishing mechanism and XMSS as a signature. And the IETF is the organization that puts out the RSC documents. They also standardized already the XMSS and LMS signature scheme. So the new schemes all come with some challenges, and that is mostly that they are much more complex and much more hardware inefficient than the predecessors like RSA or something. So for example, the key sizes are much larger, or the computations are much more expensive. And of course, the degree varies throughout the schemes, but generally you can say that the PQC schemes are more complex and more expensive on the devices. So we need to start thinking about the integration. And with QuantumRISC, we want to implement dedicated hardware accelerators that can speed up whole schemes or portions of the schemes to make them feasible for embedded systems. So now I will talk a little bit more about QuantumRISC and the RISC-V platform we chose. So there are basically two options we can go, two ways we can go here for the implementation of hardware accelerators for quantum PQC schemes. So the first one is to implement a full scheme in hardware, which we can then start from our RISC-V platform using a custom instruction. For example, we would have then a encryption function, and that just does the whole thing. Of course, the problem there is that it requires quite a lot of hardware logic, and it's quite complex to implement the whole scheme in hardware. But on the plus side, it's very fast if we do it correctly. And the other option would be to implement building blocks in hardware, which are heavily used throughout the schemes. And the advantage here is that we can share these building blocks throughout multiple schemes. That is, we don't have to fixate to one scheme now and then use it for the entirety of the lifetime of the device, but can rather build or develop our building block in a way that we can share it throughout multiple schemes. And if it turns out that throughout the standardization one of these schemes is dropped, then we can just use another scheme with the same building block in hardware and then use that. The disadvantage, of course, on that is that it might be a bit slower, but generally this is the preferred approach for the QuantumRISC project. And for the development platform, we chose the VexRiscv CPU, which is a 32-bit RISC-V processor with 2 to 5 pipeline stages. It has an instruction cache, data cache. You can run Linux on it if you want, and it's completely open source and can be run on FPGAs. But most importantly, it's highly configurable. That is, we can just implement our building blocks and just build them into the VexRiscv processor and use them seamlessly within. The VexRiscv core is completely written in Spinal HCL, which is a custom-made hardware description language based on Scala. And it is important to note that Spinal HCL is not some kind of high-level synthesis tool, but rather an actual hardware description language, much like VHDL and Verilog. But due to some neat language features, it's very, very handy and much more versatile than VHDL and Verilog. And you can imagine the VexRiscv core as an arrangement of stages, for example, fetch stage, decode stage, execute stage, write back stage, and memory access stage. And then you can use plugins to fill these stages with logic. And the whole core, the whole VexRiscv core is implemented by using plugins. So here on the right, you can see a part of the plugin folder from the GitHub project. And you can see, for example, the fetcher.scala implements the fetch logic. And there's also a branch plugin which implements the branch behavior. And it is very easy to create new plugins that perform custom tasks, and therefore it's very easy to implement, for example, accelerators for cryptographic procedures. And in each of these plugins, you can access any state register. So it's not like VHL and Verilog where you have to route the register throughout multiple modules, and then it becomes all very cumbersome. But it's very handy, very clean, and yeah, therefore it's very easy to implement new plugins. So if you're interested in the Quantum RISC project, you can visit the homepage, and there's also like a very extensive report on the results of the first work package, where the use cases are defined and stuff. And also we have a GitHub project for a simple benchmarking platform based on VexRiscv, where it's very easy to get started and you only get the things that are really necessary to get started. And last but not least, we also have a public virtual machine ready for download, where you can try or directly start with the hardware development with the provided toolchain. And the VM also comes with an extensive documentation, so it's very easy to get started there. Yeah, and of course you can also write me an email and ask everything, or if you have questions right now, I'm happy to answer them for you. Yeah, thank you for listening, and yeah, I'm happy to answer your questions.